Hello, this is Eric Ward, and for today's lecture, we'll be talking about model selection, cross-validation, and performance of different time series models. So the three things we'll highlight is really what are some different approaches for evaluating different models. So this is known as model selection. The second is, given our data, can we use some metrics like cross-validation to evaluate how well the models are able to predict other new data sets? And third, can we use our time series models to do forecasting or hindcasting and evaluate or quantify the performance of different models on a relative scale? So first, we'll ask, how good are our models? So we might build several different models or evaluate several different models for a given data set based on either different hypotheses or mechanisms that we think are responsible. And so this could be different models of density dependence or different models of stock recruitment for a given fish population. And then once we've got our model, we might be interested in looking at different diagnostics or summaries of fit. And this might also influence the list of models that we're building. So for example, we might fit a simple model without autocorrelated errors. If we see autocorrelation in the residuals, we might want to add a different parameter. And so to explain the variability in the residuals that we're seeing, and that iterative model building process will create a list of new models that we might want to consider. Once we have our list of models, we are then interested in how well they can explain the data that we have. So we might evaluate the models just on their ability to explain the data, or we might want to look at the model's ability to both explain the data and their ability to predict future data. Or we might not care at all about how well they can explain the data. Maybe we just care about their predictive abilities. And so in this case, we're thinking about, in a forecasting sense, we could think about including out-of-sample data in the future, which is often thought of as forecasting, or out-of-sample data from the past, which could be thought of as hindcasting. So to really think about how good our models are, I'm going to start with just the simple data set from the Mars package. And this data set is known as the Harbor Seal WA data set. It's a collection of harbor seal abundances from Washington State. Each time series is associated with a different stock. And so in this case, we have the log transformed abundance from the San Juan Island stock. And in log space, this population is basically increasing linearly, which corresponds to exponential growth in a normal space or untransformed setting. I think most people in the class are probably familiar with sum of squares, or R squared. Remember that R squared is just 1 minus the residual sum of squares divided by the total sum of squares, where the total sum of squares is the variability in the data. The sum of squares here just represents the squared difference between the data, the y sub I, and our expected data, or expected value of the data from our model, which is the expectation. Then we calculate that squared difference for each data point and sum them across data points to calculate a total sum of squares. Models that have low sum of squares or models that fit the data really well will have small sum of squares because their difference between the data that we observe and the expectation will be essentially zero. And we can see that, as I said before, there's this correspondence between sum of squares and R squared. If we fit a lot of different kinds of models in R, for example, with regression, we can look at the summary of these model objects and see that the model statistics are often reported in terms of the R squared at the bottom, which is 0.84 for the multiple R squared, or 0.83 for the adjusted R squared. And what these values indicate are that the model does a pretty good job explaining the data. R squared of 0.8 or higher is actually pretty good in fisheries and ecology. But the potential for just relying on sum of squares or the residual sum of squares is, as we start to add more parameters and develop more complex models, inevitably they have to reduce the sum of squares. And so they'll keep fitting the data better and better the more parameters we add. And there's no cost or penalty associated with having too many parameters in our model. So this introduces the idea of model selection. And in fisheries and ecology and other fields, there have been a lot of different metrics that have been proposed to kind of overcome this problem and introduce some penalties for introducing too many parameters or making our models too complex. And the two ideas or theory behind this is based on Occam's razor and the principle of parsimony, which is that we want to really choose the simplest possible model for our data set that explains the data pretty well. Another way to think about this is that we want to choose a model that minimizes both the bias and the variance. And so the way that this is often shown is that we have a squared bias on the first y-axis and a squared variance, or just a variance on the second y-axis. And as we add more parameters to our model and make the model more complex, we're going to reduce that bias. But at the same time, the cost of reducing that bias is that we're going to be increasing that variance. And so we want to really choose a model that really hits the sweet spot here and minimizes both the bias and the variance simultaneously. The challenge is that how do we weight the bias and the variance, and that's really where the different model selection approaches differ, is how we're weighting the penalty for too much bias versus too much variance. So the first model selection approach that we'll talk about, which is probably something that everybody here has used before or is at least familiar with, is what's known as AIC, or Akaiki's information criterion. And what AIC tries to do is balance the goodness of fit, so how well the model fits the data, against how many parameters or how complex the model is. And AIC is really based on this first term is the deviance. The deviance is also calculated as twice the negative log likelihood, which is what this term represents. Deviance, we can think about deviance as a measure of the model fit to the data, where lower values are better. And so lower values are better because in a maximum likelihood setting, we want to find the parameters that maximize this likelihood function. And maximizing the likelihood is equivalent to minimizing the negative log likelihood, or minimizing the negative log likelihood, or minimizing the likelihood. And so in this case, lower values are better and associated with better fits to the data. And many of these IC or IC approaches to model selection, like AIC, differ in that they all include this deviance term representing the model fit. Where they differ is how the penalty for too many parameters is introduced. And so for AIC, for example, the penalty term here is the second part of the formula, the plus 2k, where the penalty is 2 times the number of parameters, k. One of the things with AIC that we can think about is that if we have a time series with 3 data points or 3,000 data points, we don't see the sample size, n, introduced into this formula at all, because it doesn't factor in. Because of that, there have been a number of different approaches to develop extensions of AIC. One of the most common is this, what's known as the small sample AIC. And Burnham and Anderson and other authors suggest that when you have a sample size smaller than, say, 30 data points, it's probably a wise choice to use this small sample variant. And so we see here that n, the sample size introduced, is in the denominator of the formula. One of the things that we can see here is that this penalty, this extra penalty term, shrinks as n gets larger. And so as n gets to be infinity, this denominator would get very, very large, and this whole term would basically cancel out. So AIC, the small sample version of AIC, or AICC, will eventually converge to AIC as our sample size gets larger. So when we think about AIC, as we said before, AIC tries to find the best model that is able to predict data generated from the same process that generated your observations. But a downside to AIC is that it has a tendency to overpenalize complex models more so than other metrics. We can think about AIC also in kind of a likelihood ratio test framework where we might want to use a likelihood ratio test statistic to compare two different models. Using AIC to basically perform the same test is equivalent to doing a significance test or setting your alpha from 0.05 to 0.16. So there's alternatives to AIC that are not quite as they don't have this tendency to overpenalize as much. One of them is what's known as the Schwartz or Bayesian information criterion, and so you'll see this in the literature described as either SIC or BIC. A key point here is that even though it's called the Bayesian information criterion, it's not actually Bayesian. It does rely on this Laplace approximation to the posterior distribution, which assumes that the posterior density is normally distributed. And in the thinking about the significance test here again, this alpha of the associated with the significance test becomes a function here of the sample size. And more so than AIC, BIC is a measure of the explanatory power of the model. And so rather than balancing this explanation versus prediction trade-off, BIC is more associated with just explaining the data that we have. And because of this, BIC, using BIC as a model selection statistic, has the tendency to underpenalize complex models. So it's kind of in contrast to AIC. So we can compare and contrast these philosophical differences where AIC, or the small sample version of AIC, really tries to choose a model that approximates reality, given that or tries to find a process that is similar to the process that generated the data that we observe. But it doesn't necessarily assume that reality exists or the truth exists in the set of candidate models that we have. An important contrast with BIC is that BIC assumes that one of your models is truth. And so as you increase your sample size and collect more data, the weight or the evidence associated with one of the models in your list will eventually converge to 1 or 100%. And so eventually your data will support one model all over all others, which is assumed to represent truth. One of the useful things about AIC is that it's become pretty widespread, and so a lot of the packages that we're using in this class for time series models and regression and nonlinear models all have AIC supported. So the AIC function can be used to call, we can pass in a regression model object with LM, a GAM with in the MGCV package. It supports TMB, or packages in LME4 and the forecast package. So all of these are ways to get AIC out very easily instead of just calculating it yourself. So some folks may also be interested in Bayesian model selection, and we'll touch on this later in the class, but it's largely beyond the scope of kind of this introductory material. As a quick overview, we have several options. We have Bayes factors, which are approximated by BIC, again, because of this Laplace approximation. Bayes factors are potentially problematic because they can be pretty challenging to calculate for complex models. They can also be pretty sensitive to the choice of prior distributions. A second approach is to use the deviance information criterion, or DIC. And so this was originally developed in a 2002 paper by Spiegelhalter. And DIC is particularly easy to get out of several widely used programs like Bugs and JAGS. And DIC has been proposed as this alternative to AIC, where we're trying to minimize both the bias and the variance simultaneously. So like AIC, DIC is also a function of this deviance term. And then this penalty representing the effective number of parameters. The effective number of parameters in DIC differs slightly from AIC in that with a model where we're applying AIC, we have this number of parameters k that we can calculate for any model. And so AIC is really most often applied to models with just fixed effects. And so what that means is that we can write down the model and then calculate all the parameters on our fingers, and it's a discrete number. Where AIC doesn't work so well is where we have hierarchical or state space models where the number of latent parameters that we're estimating might not be a discrete number. It might be a continuous number. And so in this case, DIC kind of overcomes this obstacle with AIC in that it's applicable to both models with fixed effects and also hierarchical models. And so this PD parameter, the effective number of parameters, doesn't have to be an integer. It doesn't have to be discrete. There's two ways to calculate the effective parameters, this P sub D. The first is based on the difference between the expected deviance of the model and the deviance of the expected or the mean posterior distribution. Or second, we can calculate the penalty term based on the variance of the deviance divided by 2. And so this was proposed by Gelman in 2004. There's some philosophical and some big estimation differences between the Bayesian and the maximum likelihood approaches to model selection. A key point is just that the maximum likelihood methods are taking this likelihood function and maximizing it over the parameter space, where with the Bayesian methods we're doing integration instead of maximization. So the Bayesian methods are integrating over the entire parameter space or this likelihood function and asking what values are best on average instead of which values are best. Many of the maximum likelihood methods that we've discussed so far, like I said, were really designed for models with fixed effects. And so when we have this correlated parameters or nested or hierarchical models, there have been variants of AIC that have been proposed to deal with those classes of models, but they're not easily accessible in a lot of the packages that we're using for this course. Okay, so that's what we wanted to talk about with model selection. Moving on to the next theme, thinking about cross-validation. There's been recently kind of a huge focus in fisheries and ecology in thinking about quantifying prediction of different models, and so this is just a list of some of the great papers that have come out in the last couple of years. I encourage everybody to take a look at these. And thinking about prediction and forecasting especially, we can think about a number of different resampling techniques that might be useful in evaluating the predictive ability of models. I should say too that there's no single right answer that will fit all cases. It really is kind of case specific depending on the problem and the prediction question you're interested in. Some of these might be more useful than others. So starting with a jackknife. The jackknife is often used where we will hold out each data point in turn and recompute some test statistic and then average across all of those held out values. And so this might be useful for looking at calculating a variance, for example, of a prediction or a mean or median or some other statistic. We could do a bootstrap. And so a bootstrap is similar to the jackknife, but a bootstrap more often involves resampling the data. Third, we could think about cross-validation. And so cross-validation can be thought of this is often expressed in terms of k-fold cross-validation. The folds represent divisions or partitions that we take our data, we divide it into k partitions, and then instead of holding out each data point, we hold out a partition one at a time and look at how well the other partitions predict the kth set of data points. One of the interesting features of this k-fold cross-validation is that if we have a single data point held out at a time, so just it's just a k-fold cross-validation where k is also n, the sample size in our time series, then this leave one out cross-validation converges to AIC and will give us the same answer in terms of selecting the same model. So the last kind of resampling that we could think about would be just a data split. And so in this case, we would take our data, we would split it into a test and a training set. And in this case, we might select our training set would be everything up to the last 5 data points. Our test set would be the part of the data that we would be predicting to. In this case, it could be, for example, the last 5 data points. and then we would evaluate the model's ability based on data that was not used to fit the model. So the bootstrap and the jackknife approaches are really widely used. They're generally used in the context of time series models to generate new data sets or pseudo data sets, and so we'll talk about this with the Mars package later. But with state space models especially, we have deviations or these errors to simulate both for the process model and the observation model. It's also really useful to use bootstrapping to estimate variances of predicted states or new data, and so to estimate any of these confidence intervals, bootstrapping is really useful. In both the Mars package and the forecast package, there's a few different bootstrapping routines that are available. We won't get into them now, but just a heads up that these are basically how we call them. So just to illustrate a quick example of the resampling, we'll take a data set from, there's a beavers data set which represents body temperature for 2 different beavers, and in this case I've just filtered it to be a single beaver. We have body temperature on the y-axis across time on the x, plotted down below. And what we want to think about is we'll choose to apply k-fold cross-validation here with regression. And so regression is not necessarily a time series model, but it's just a simple case, and we can extend this to deal with ARIMA models and time series models. So the first step here is to choose the model that we want to fit to the data. In this case, like I said, we'll use regression. The second is to partition the data into some number of folds, and then we'll do this fitting and prediction routine. And so in this case, we'll start simply by choosing k to be 5, so there will be 5 partitions here. We will the first line of the code is going to be to sample the data set with replacement here. That's an important thing to note. So we're sampling with replacement, and we're just sampling totally randomly here. So each data point has an equal chance of being included in every partition. And then we're going to loop through. This loop is going to be for the 5 folds. We're going to, for I equals 1 to k. For each fold, we're going to first fit the model using a regression to the data, to all data except for the partition that we're looping over for this iteration. And then the predictions are going to be made on the next line to where the new data here is the partition that was held out. And so we're doing this iteratively just 5 times, where each prediction is based on all of the other folds. Okay, so the code to actually replicate this plot is hidden but associated with this slide, so you can go back and look at it. What we have here, though, is we have our observed data as the black dots. We have just a linear model fit, which is to the whole data set, which is the gray line. Then we have our cross-validated approach. And so in this case, this is just one iteration of the whole algorithm. And what we see is that there's a pretty good correspondence between the linear regression to the whole data set and the cross-validation to each of the 5 partitions. In this case, we could also color code the cross-validated predictions based on which partition each data point was in. That doesn't really matter because the result is basically the same. And this is something that we expect because each data point here was randomly assigned to one of the 5 partitions. There wasn't any rhyme or reason to preserving the order of the time series or only sampling each data point once, for example. So some things to think about with k-fold cross-validation are how many partitions should we have? How large should k be? And this comes back, of course, to this bias variance trade-off that we were really hammering on with AIC, where when we choose a small number of partitions, or low k, we generally have low variance and large bias. And the benefit of having smaller number of iterations is that this is obviously quicker to run. The machine learning approaches generally recommend 5 to 10 partitions for a data set. And in contrast, when our partitions are high, and so the extreme case of this, of course, is where we have k is the same as our sample size or the length of the time series. When we have large k, we get low bias and high variance. And this is more computationally expensive. And so ideally, we would hit some middle ground between these two extremes. So one extension of the k-fold cross-validation that's useful is that for thinking about our Beavers data set, it could be that those results that we predicted were sensitive to which of the partitions each data point was associated with, or how our partitions were sampled. And if we were doing the analysis for real, we might want to remove any of that random sampling effect that could kind of creep into affecting the results. One way to get rid of that sampling effect is to do this iterative step where we would repeat this k-fold cross-validation approach a large number of times and then calculate the average predictions across all of these different iterations over the k-folds. There's a few different ways to do this in R that are pretty simple. You can obviously code this yourself with a few loops. It's pretty straightforward. There's also the caret package in R that's really useful for doing these kinds of analyses for you. And so in this case, just to illustrate how this is done with caret, we have to first specify exactly what we want to calculate. So the method here is going to be repeated cross-validation. The number represents the number of folds, and the repeats represents how many times we're repeating this whole exercise. Again, this is just a regression application. It's easy to extend this to every single other model that's in the caret package, which represents the vast majority of the models that we're talking about in the time series class. And so when we look at this model here, this is kind of our fit to this repeated k-fold cross-validation fit to the linear model. And what we get out of here are our estimates and which are going to be the averaged estimates across all of the different repeats or realizations. We have our coefficients and again the standard errors and sum of squares, just as we would with regular regression. So what about for time series data? I think that a couple points that I mentioned before that we need to hit on are that when we're taking those time series of Beaver body temperature and assigning them to partitions, there were two things that we did that were potentially not really appropriate for time series data. The first was that we sampled with replacement, and so every data point could be used more than once potentially. And the second was that the assignment of data points to partitions was totally random, and so this kind of destroyed time series order. We might want to preserve that, especially if we're interested in being able to describe the autocorrelative properties of the model that we're using. And so one approach to deal with cross-validation for time series data involves what's called forward chain cross-validation. And so the way to do this is to only evaluate models on data that comes later. And so we would divide the model into a training data set and a test data set. And so in this case, we could think about establishing, say, 4 folds of a given data set. And so in fold 1, we would say divide the data into 5 equally sized bins. We would use, for fold 1, the training data set would be the data from the first fold, and the test data set would be the data from the second fold. For fold 2, our training data set would become larger, with the training set being the first 2 folds and the test set being the third. And this would proceed iteratively so that eventually, for fold 4, the training data set would represent the first 80% of the data, and the last test data set would represent the last 20%. Okay, so as an example of how to do this, so we're going to still use the beaver body temperature data, but what we'll do is instead of using that regression model, which is probably not really even appropriate for the body temperature, we'll use an ARIMA 111 model. And so the ARIMA 111 model, just to reiterate, is that the P, the Q, and the difference parameters are all set to 1. And so this means that we first difference the data, and we're including a single MA and a single AR component. We're going to, again, use 5 partitions in order, so there will be, we'll divide the data into chunks, where each chunk represents 20%. We'll create a partition based on this line of code here, which is just going to divide the data into those equally spaced chunks. And then we'll iterate through the data set, fitting the model to each and doing forecasting. There's a number of ways to do this. I think that this is just some pseudocode that I put together that will do it really simply in a loop. You can easily extend this to deal with other time series models. But for each of these, what we'll do is just we'll fit our ARIMA model to the data, to any data that was before this partition. And then we'll make our prediction using just the forecast function or forecast library, and evaluate. We'll use the mean forecast here. You could change this to do any other metric that you wanted, but we'll just save these predictions across those iterations. So we talked about the Bayesian model selection. Bayesian cross-validation is also something important to think about. So the leave one out cross-validation approach is definitely also available in the Bayesian setting. I think that the developers of Stan especially have been working on the leave one out cross-validation approaches in a Bayesian sense. There's also a WAIC, or the widely applicable information criterion, that's become commonly used. And both are available in this Loo package in R. And so as we move forward in the class and start using Stan, we're going to also be using some of these cross-validation approaches in a Bayesian setting because they're really widely used. And ultimately, the cross-validation approaches, I think, are becoming very popular because that's really what we really want to see a model that can predict out of sample data really well. And there's some additional reading here on the Loo package, but both in a maximum likelihood and Bayesian setting, we want to choose a model that has good out of sample prediction. And so we'll be touching on this more as we kind of work in a Bayesian models in the future. Okay, so for the last bit of material for this lecture is we'll talk about some prediction and how do we evaluate predictions, how do we evaluate forecasts across different models. So I think that Eli talked about this in a lecture last week, but let's think about forecasting with ARIMA. And so again, we'll take an ARMA. In this case, this will be an ARMA 1.1 model. We have a time series here of global temperature data. And as Eli said, we can use the ARIMA. There's 2 ARIMA functions that we can use where we can get equivalent answers. And so we won't include a seasonal component here because these represent just annual data. And the order here will just be, we'll do a first differencing because of that non-stationary trend in the mean that we saw. And we'll include a single AR and a single MA component. The forecast length here is chosen by H, and so in this case we'll just set H to 10. You can choose to set that to whatever you want, but this will just represent we'll be forecasting 10 years in the future. Okay, so if we do this simple forecasting, we can take a summary of the model object and get out a bunch of different metrics, including some error metrics that are cut off at the bottom here. But it will give us the out of sample prediction. If we plot what the forecasts from this ARIMA model look like, as Eli showed, we get this this object where the predictions here are going to be essentially have no trend because we've first differenced everything and that don't have a seasonal component. But then what we might be really interested in is how do we calculate the forecast performance, given that we forecast 10 years in advance. How well do those 10-year forecasts represent reality? So there's a number of, like with model selection, there's a number of different approaches for evaluating forecast performance. One of the most widely used is known as mean square error, or MSE. And so mean squared error looks very similar to sum of squares in that we're evaluating how well the data in question, so this x sub t, differ from the predictions, which is the expected value of x. We take those squared quantities and average them across all the data points. So in addition to mean squared error, root mean squared error, or the square root of this quantity are also very common. Like with model selection, we're also interested in the principle of parsimony. So the trade-off between bias and variance for forecasts is also important, just as it is for model selection. And we can actually just rewrite that mean squared error as the sum of the variance of our predictions plus the bias between the data that we observe and our predictions squared. And so again, that's just that variance bias trade-off that we've seen for the second or third time today. Again, smaller mean squared error, like with sum of squares, is just this lower bias and variance summation. So in thinking about how MSE, or mean squared error, can be applied to time series models, mean squared error and any of the forecast metrics that we're thinking about can be calculated for single data points if we're just interested in one step ahead predictions. They can be calculated for entire time series, and so this might represent how well an entire time series fits a single data set that you have. Or it could be used for out-of-sample predictions, so just based on future forecasts, for example, where the held-out data are not being used to fit the model. And this is a really important step. There's no right answer again. It really depends on the case study and the question that you're interested in, but whether you use a single data point to evaluate a prediction or an entire time series really matters. So, for example, if we were trying to forecast population productivity 5 years in the future, you could imagine developing a model where we're making these 5-step ahead predictions, and we only use that 5th data point as the prediction to evaluate mean squared error with. Another way that we could think about setting up the model would be, if we're doing these 5-step ahead predictions, we could hold out the last 5 data points and use all 5 of those. And in that latter case, we'd be more interested in the path or the trajectory that we were forecasting rather than just what the ultimate prediction was 5 years in the future. Okay, so another couple approaches or extensions of mean squared error are root mean squared error. And so again, this is just the square root of the root mean squared error. Square root, this is a typo, it should be the square root of MSE. Like mean squared error, root mean squared error is on the same scale of the data, and it can also be referred to in the literature as the root mean squared deviation. There's two other metrics down here. We have mean absolute error, or the mean absolute deviation, or median absolute error. And so these are just taking the instead of there, you can see that instead of this term being squared, it's just the expectation of the absolute difference between the data and the prediction, and this is the median absolute value of between the data and the prediction. And so those are just slightly different. We don't have the quadratic term appearing in either. So where this gets to be important is that when we're applying these different models to different data sets that are occurring on different scales, metrics like mean squared error or root mean squared error will be driven by time series that's larger in magnitude. And so what that means is that if we had time series here for 2 different species of fish, and we were including both in our forecasts and using them both to simultaneously evaluate model performance, population 1 here, there's, it's substantially larger than population 2. So the deviations in our predictions for population 1 would have more of an impact than would deviations from the differences between predictions and observations for population 2. So they're not balancing those two populations equally in terms of their errors. What that really motivates us to think about is that, are there some scale independent measures of performance? And so another kind of extreme value of this is that, this is a plot of chicken wing sales weekly, going back to, this is for the year 2013. This is for a whole calendar year. You can see for most of the year, sales are pretty flat. Then we have the spike that's associated with the Super Bowl. And so when we have these anomalies in time series, errors associated with these anomalies are also potentially going to have more of an impact than errors associated with individual data points. And so, like the example before, where we had one population that was weighting the predictions more than another, we also have data points like this Super Bowl anomaly that will have more of an impact and more weight than other data points in the time series. So that introduces the next kind of flavor of forecast error statistics, are what's known as percent error statistics. And so the percent error statistics are just calculated as the error, so the difference between our predictions and observations, scaled by the data. So in this case, we can have just the percent error. We can have a statistic known as MAPE, which is the mean absolute percent error. Again, we just take the absolute value and the expectation over that, or the root mean squared percent error on the bottom, which is the squared percent error, the expectation of the squared percent error, and then that quantity we'll take the square root of that. So percent error statistics are useful and widely used, but going back to our last slide, what happens when y equals 0? Well, you can see that the percent error calculation here, when y equals 0, this term really becomes undefined, which is potentially problematic. It's widely known that the distribution of these percent error statistics tends to be pretty skewed, and it has long tails. A problem with the MAPE statistic in particular is that it tends to put higher penalty on positive errors more so than negative errors. So this and a number of different other properties of these statistics are reviewed in this great paper from 2006. And I think that there's been a lot of good work kind of on developing newer metrics for evaluating performance. One of these are what's known as scaled error statistics, and so scaled error is defined as the error, which is the difference between the observation and prediction, again divided by the scale down here is the difference data. So this is essentially what we would get from a random walk averaged over all values. And so the denominator is the mean absolute error from a random walk model. And so it's naive, and that's kind of the simplest possible model that we could have for a time series. A problem with this method in general is that it doesn't really allow for having missing data, because we can't take the difference between yi and na. So that's one downside. We can also use these absolute scaled error statistics, which are the absolute value of the error statistics, or the mean absolute scaled error statistics, MACE, also becoming more commonly used. So when we interpret the absolute scaled error, ACE, or the mean absolute scaled error, MACE, all values are relative to that naive random walk model, and so values that are smaller than 1 suggest that the performance of the model that we're evaluating is better than a random walk model. That's really what we want to see. When values are greater than 1, it indicates that our model performance is actually worse than a random walk model, and that's really not what we want to see. So to implement this in R, I thought we'd just kind of run through a quick example. So we'll use this air miles data set, which represents the number of miles flown in R by year. We'll hold up the last 3 data points, and we'll log transform the data here just because these data tend to be pretty skewed, and they're strictly positive. So we'll fit this. We'll use the AutoArima function to fit our a wide range of models and select the best one. And so we'll forecast the model 3 steps ahead from that fitted model. And so in this case, we have the best model is an ARIMA 011 model with a drift term because the time series is non-stationary. And so this represents kind of the 3-step ahead forecast. This air.forecast is the object that we're forecasting. And then what we can look at is there's this accuracy function that is can be used in calculating a whole suite of different error statistics here. So we have, in this case, we have 6 that are coming out by default. And what we'll do here is our holdout will be, our test data set will be 3 data points, and we'll evaluate, so this would be, in this case, if we want to evaluate the test statistic for the last 3 data points, we could set this function to be, to have the test argument would have a value of 3. In contrast, if we wanted to just hold out the last data point, for example, we could fit the model with the same data, but then our holdout would just be set to 1. And so we can look at how these differ. As I said before, if we want to look at the ACE or MACE statistics, we want to have those values be smaller than 1 when they're larger. It would suggest that we would be just as fine with a random walk. So just to summarize, the raw statistics, so the raw statistics being mean squared error or root mean squared error, which are on the same scale of the data, shouldn't be really applied to data of different scale. And so I illustrated 2 different applications where we had 2 different time series which were on a different scale, or a single time series where we had some outliers or anomalies that might have a lot of weight. Second, the percent error metrics, and so metrics like MAPE might be skewed and undefined for real zeros and potentially problematic. And then third, that these scaled error metrics like ACE or MACE have been shown to be pretty robust, and they've been widely used in meta-analyses of many data sets, including things that we've published on fisheries problems. And so I think that this field is still evolving, but these things are a big improvement on some of these past metrics. And with that, we'll take any questions, and thank you.